In this video, we are going to learn how to find the curvature of a vector function. Essentially, we're going to be able to calculate how curved the graph of a vector function is at a point. So, given a smooth vector function r of t with unit tangent vector, capital T, and parameterized with respect to arc length, the curvature of r of t is defined as k, okay, this is our symbol for curvature, equals the derivative of t with respect to s. So this is the derivative of the unit tangent vector with respect to arc length. And essentially what we're measuring is how does the unit tangent vector change with respect to arc length. So to give you a visual, right, if we drew a curve like this, okay, let's say there is one unit tangent vector, and let's say here would be another unit tangent vector, and the movement along the curve we'll define as ds, right, the change in arc length. Okay, how is the direction of that unit tangent vector changing as we move over a small portion of the curve? And remember, unit tangent vector just gives us direction because unit means the magnitude is 1. Now, using this definition to compute the curvature would be a little bit of a challenge, so we're going to talk about that in the coming slides. So curvature is a measure of how quickly a curve changes direction at a point. The unit tangent vector defines the direction of movement, and the rate at which it changes with respect to small steps ds along the curve is a good indication of how quickly it turns or curves. Right, so just formally defining what I was speaking about as I drew that diagram. So some pictures below. So the graph of a line. This would be an example of a curve that has 0 curvature. If you drew a few unit tangent vectors, they would all point in the same direction, so the change in direction would always be 0. So 0 curvature. Now, as we look at our circles on the right-hand side, the smaller circle actually has the larger curvature, right? So the small circle's curvature, so small, let's fix that. I'm not sure why I changed colors, so the small circle curvature is actually going to be greater than the large circle curvature, using that K symbol to denote curvature. And if we think about it, if we move along the same arc length on either circle, the unit tangent vector is going to change directions more quickly for the smaller circle than it is for the larger circle. Right? The circle is less curved the larger it is at a given point. And if we just drew, let's say, some type of curve like this, right? It starts out with a curvature that's closer to 0, and as we move along the curvature would increase as we get to that innermost point, right? The graph is getting more and more curved as we go in. Right? So that gives us an intuitive sense of what curvature is. But now let's talk about computationally. So since reparameterizing in terms of arc length can be challenging, it would be easier if curvature was defined in terms of t. So right now the definition is the derivative of the unit tangent with respect to arc length. So if we wanted to use this definition, if you think back to the arc length video, we would have to set up the arc length function, which I have here, s of t equals the integral from t naught to t of the magnitude of r prime of u du. Then we'd have to use that to get t in terms of s, plug that back into the vector function. Now you have the vector function in terms of s. Then you would find your unit tangent and proceed on. Right? That's quite a number of steps to get to that point. So our goal is, can we take this definition and instead define it in terms of t? So the key in doing that is differentiating the arc length function by the fundamental theorem of calculus. So if we differentiate the arc length function, we have ds dt equals the derivative of the integral, which is just equivalent to the magnitude of r prime of t. So ds dt is the magnitude of r prime of t. That's a quantity that we know how to find. We found it for numerous examples so far. So now let's go back to this definition, and we need to manipulate the definition a bit to get to a point where everything's in terms of t. So let's suppose that the unit tangent vector is in terms of t, because often, right, we write t of t. So it is. So if we were to use the chain rule, we can rewrite this as the derivative of the unit tangent with respect to t. And now, based on the arc length function, s can be a function of t, t can be a function of s. So let's use that latter definition, that t is a function of s, and by the chain rule, we're going to have to differentiate t with respect to s. So now we can rewrite this expression inside, so that's dt over dt, so the derivative of the unit tangent with respect to t over the derivative of arc length with respect to t. Now this is getting to a point that is more useful for us, since the derivative of the unit tangent with respect to t, that's just t prime of t. And as we established from differentiating the arc length function by the fundamental theorem of calculus, that's going to be the magnitude of r prime of t. And all of that's inside the magnitude, so I'll just put the magnitude also around the derivative of the unit tangent. So now we have a definition in terms of only t. So this is better than the original definition of curvature, which was the derivative of the unit tangent with respect to arc length. Now we have it defined as the magnitude of the derivative of the unit tangent vector over the magnitude of r prime of t. So this is helpful. If your unit tangent vector is nice, then this definition can work out pretty easily. But more often than not, the definition or the formula we're going to use to compute curvature is as follows. Curvature being defined as the magnitude of r prime of t crossed with r double prime of t over the magnitude of r prime of t cubed. Right, if you want to think of it in terms of motion, velocity crossed with acceleration, the magnitude of that vector, over the magnitude of velocity cubed. This is just easier because often if we're given r of t, the vector function, we can just differentiate, find r prime, find r double prime, do a cross product, some magnitudes, and then get our curvature definition. The derivation of this is interesting to look up, but I'm not going to dive into that in this video. For a plane curve, so let's say we have y equals f of x. So y equals x squared, right? A curve rather, in the xy plane. The formula for curvature would be the magnitude of the second derivative over the magnitude of 1 plus the first derivative raised to the 3/2 power. Now, this is a nice formula if we have y equals x squared, but to be honest, I really only use this formula here with the r prime and r double prime. If I was given y equals x squared, the way I use the first formula is to parameterize the curve, something that we have done before. So I would parameterize this as r of t is t f of t 0, right? So that would be the parameterization of a curve in two space. So let's say it was y equals x squared. We would have t squared, 0. Now we've defined a vector function, so now we can go and use that formula. Okay, so really this singular formula can be used for any of our computations. Could we use the one in terms of x? Of course. And could we use the one in terms of the unit tangent and its derivative? Yeah, we can definitely do that too. Really, if the unit tangent vector is given to us, this might be a good approach, or if it's easier to find than doing this cross product. But we have options. But for the most part, you're going to see me use this cross product formula to compute the curvature. So find the curvature of r of t being equal to e to the t, e to the negative t, t squared of t. So we're going to use that cross product formula. So we need r prime of t, which is equal to e to the t, negative e to the negative t, and the square root of t. And then our double prime of t would be e to the t, negative, negative, so positive e to the negative t, and 0. Now we need to find the cross product of r prime of t and r double prime of t. We are taking the magnitude, so the order of the cross product is not going to matter. Typically, we're just going to do r prime cross r double prime because it's easier. But if you did it in the reverse order, the magnitude would be the same. So e to the t, e to the negative t, 0. Okay, so our cross product vector here is 0 minus square root of 2 e to the negative t, and then 0 minus square root of 2 e to the t, but the j component is negative, so that'll be positive square root of 2 e to the t, and then e to the t times e to the negative t, we add exponents, so that's going to be e to the 0, which is 1, minus negative 1, so plus 1. Now we need to find the magnitude of that vector. So the magnitude of r prime of t cross with r double prime of t equals the square root of negative square root of 2 e to the negative t squared plus square root of 2 e to the t squared plus 2 squared. So let's see. That's going to be the square root of 2 e to the negative 2t plus 2 e to the 2t plus 4. Now when this happened in our arc length examples, we had to dive into the algebra a little bit deeper. Let's pause here. Let's see if we get some simplification when we go to compute the curvature, and if not, we can always start diving into some more algebraic manipulation. We also need the magnitude of r prime. So I'll use a different color here. So the magnitude of r prime of t is equal to the square root of e to the t squared plus negative e to the negative t squared plus the square root of 2 squared. So the magnitude of r prime of t is equal to the square root of e to the 2t plus e to the negative 2t plus 2. We have our quantities, and we can go to compute curvature. So curvature is equal to the magnitude of the cross product, so the square root of 2e to the negative 2t plus 2e to the 2t plus 4 over the magnitude of r prime of t, which is the square root of e to the, is it 2t or, yeah, 2t. E to the 2t plus e to the negative 2t plus 2, and we're going to raise that to the third. So, if we notice, we can factor out a square root of 2, and that would leave us with e to the negative 2t plus e to the 2t plus 2, and then over square root of e to the 2t plus e to the negative 2t plus 2 to the third. And we can simplify. That's the same expression inside of the square root in both the numerator and the denominator. Right, so then we can make this to the second power, which then really means that curvature is just the square root of 2 over e to the 2t plus e to the negative 2t plus 2. And we're okay to leave it like this. We don't need to do any manipulation, factor, because we've eliminated the square root there. Okay? So this gives us curvature as a function of t. And if we wanted to compute the curvature at different points along the curve, then we would plug in the various t values. So the curvature at, let's say, t equals 0 for this curve. We would have square root of 2 over 1 plus 2, so 4. Right? So at t equals 0, the curvature is square root of 2 over 4. And that value is going to change as we move along the curve. Our next example, find the curvature of the helix r of t being equal to cosine t sine t t. So this would be a good moment to pause the video, try the computation on your own, and then play the video to see how you did. Okay, so hopefully you gave this a good try. So let's see, r prime of t is equal to negative sine of t cosine of t 1. R double prime of t is equal to negative cosine t negative sine t 0. R prime of t crossed with r double prime of t is equal to I, j, k. Negative sine of t cosine of t 1. Negative cosine of t negative sine of t 0. So we get 0 minus negative sine of t is sine of t. And we have 0 minus negative cosine t is positive cosine of t, but the j component is negative, so negative cosine of t. And then sine squared of t plus cosine squared t, which is just 1. So now we need to find the magnitude of that cross product vector. So the magnitude of r prime of t crossed with r double prime of t equal to the square root of sine squared t plus cos squared t plus 1 squared is 1. Again, we have that Pythagorean identity sitting there. So we have the square root of 1 plus 1, which is the square root of 2. Now back to the top, we need the magnitude of r prime of t as well for our computation. So that's going to be the square root of negative sine t squared plus cos t squared plus 1 squared. Wrote it out a little differently than I did in our last magnitude, but that's going to be square root of sine squared t plus cos squared t plus 1. Again, Pythagorean identity, so that's 1, so square root of 2. Okay, so this should make for an interesting curvature computation. So the curvature is the magnitude of that cross product, which is the square root of 2, over the magnitude of r prime of t, which was also the square root of 2, but we're raising that to the third power. So that means we really just have 1, right? Because the square root of 2 here simplifies, that's going to be squared. So that's just 1 over 2. Now, if we think about this for a second, the answer actually makes a lot of sense. A helix has that circular motion as it moves along, in this case, the z-axis, right, based on how this helix is defined. And the circle, if you think about the curvature of a circle, it should be constant throughout the circle. So at any point along the helix, the curvature is going to be 1/2. So this curve is an example of a curve that has constant curvature. At any point, the curvature is going to be 1/2. Find the curvature of r of t equaling to 1 e to the t squared at t equals 1. So I wanted to include this example because if they give us a point to evaluate the curvature at, it actually makes the computation a bit easier. So we'll start by finding r prime of t, which is 0, e to the t, and 2t. And then r double prime of t is equal to 0, e to the t, 2. Now, there's still a lot left for the computation of curvature, but there's no calculus left. We've done all the differentiation that we're going to need to do. The rest of the computation is cross products and magnitudes. And the reason I'm highlighting this is if we're done with the calculus, done with the differentiation, we can plug in t equals 1 now. So instead of working with vectors that have t's in them, we can work with constant vectors when we go to do our cross products and our magnitudes. So we can evaluate r prime at 1, which is going to be 0, e, 2, and r double prime of 1, which is going to be 0, e, 2. Now, I included this example as well because these vectors are the same at t equals 1. And if we remember, the cross product of two vectors that are the same is going to be the 0 vector. So r prime of 1 cross r double prime of 1 is going to be the 0 vector, which means that the magnitude of those vector of that cross product vector rather is going to be 0. And then curvature is the magnitude of the cross product vector, which is 0, over the magnitude of r prime of 1, which is e squared plus 4. So that means the curvature is 0. So that means at t equals 1 on this curve, the graph has a curvature of 0. So it looks like a straight line at that point. Is it going to be true at other t values? Well, we'd have to compute it at other t values to make that determination. But for this particular curve, the curvature is 0 at t equals 1. Okay, our last piece of this video is talking about the circle of curvature. So the circle of curvature at a point P on a plane curve where the curvature is not equal to 0, that's important, is the circle in the plane of the curve that is tangent to the curve at P and has the same curvature as the curve at P. So a diagram would probably make the most sense here. So let's say we have a curve that looks like this. At this point, we can draw a circle whose curvature is equal to the curvature at that point. And let's say here, we can draw a circle, that's a better circle than the first one, whose curvature is the same as the curvature at that point on the curve, right? So the black is the curve. Now, why would we do that? There's a few things that we can find by defining this circle. We're going to just focus on the radius of curvature, but there is extensions beyond that that we won't cover in this video. So the radius of curvature then, the radius of the circle that I drew, or the circles, would be rho equals 1 over the curvature, right? So let's say the curvature at this point is 2, then the radius of this circle would be 1/2. Okay, so find the radius of curvature of y equals x squared at t equals 2. So this is our example of a plane curve now. So we could use that plane curve formula, or my preference would be to define this as a vector function, parameterize it. So parameterizing y equals x squared, which is the example that I gave a few slides back. So if we call x t, then y is t squared and z would be 0. So then r prime of t is equal to 1 to t 0. R double prime of t is 0 to 0. And again, they're giving us a value of t to compute the curvature and the radius of curvature at. So since we are done differentiating, the only things left are the cross products and magnitudes. We can plug in. So r prime of 2 is equal to 1 for 0. R double prime of 2 is equal to 0 to 0. So we can cross them. So r prime of 2 cross with r double prime of 2 is equal to I, j, k. 1 for 0, 0 to 0. So our cross product vector, 0, 0. 2 minus 0 is 2. So the nice part about defining the plane curve as a vector function, the cross product becomes pretty easy to compute with the zeros as the k components. So then we need the magnitude of r prime of 2 cross with r double prime of 2. So that's square root of 2 squared. So that's just 2. We need the magnitude of r prime of 2. So that's the square root of 1 plus 16. So square root of 17. So curvature, magnitude of the cross product vector is 2 over the magnitude of r prime cubed. So that's 2 over 17 square root of 17. And this problem wants the radius of curvature. So radius of curvature then is 1 over the curvature, which, if we simplify, would be 17 square root of 17 over 2. So that would be the radius of the circle that you would draw tangent to y equals x squared at t equals 2. Okay, so computing curvature, very much reliant on being able to take a cross product and find the magnitude of vectors. We looked at a few where we defined the curvature function in terms of t, and we'd be able to use that function to evaluate the curvature at any point on the curve. Then we looked at an example where they asked for a specific curvature. That made the computation a bit easier since we worked with numeric vectors instead of vectors in terms of t. And then the last thing we define is the radius of curvature, which is the example that's on the screen right now. So it's going to take a bit of practice with the curvature, but once we get comfortable with that formula, it's just a matter of finding all the necessary vectors, computing the cross product, and finishing the problem out.